The answer's not inside your book, I heard her say. Listen to your data and let them show the way. If you listen closely, there's secrets they'll betray. There must be 50 ways to clean your data.
Well, here we are again, talking about statistics. We're going to pick up where we left off last week. We had done a regression equation, and we're going to build upon the model that we created, adding new variables, which is called multiple regression. We'll be using JASP primarily, but I'll also give you some examples in SPSS that we can use as a comparison. So what we have learned from experience is that when you think about job satisfaction, there are many things that can affect job satisfaction. Last time we looked at burnout as a predictor, but there are many other things that could affect, predict job satisfaction. And so what we're going to do is add some more variables into the equation that we built, and we're going to see what adding additional variables does to our predictive ability. So we're going to use the same job satisfaction.sav data set that we used last time. So use that same data set, and that's the one that you would download it to your desktop, and then you would open up JASP first, and then go through the steps to open that in JASP. Once you've done that, you're ready to actually begin the analysis. So let's review the data. In this case, a boss was interested in predicting job satisfaction from burnout, compassion fatigue, and compassion satisfaction. We have data here on 200 counselors. The outcome is job satisfaction, and we're going to predict that based upon their level of burnout. That was the one variable we used last time. Compassion fatigue, which is theorized to be a form of burnout, where if you are working as a counselor, or really anyone who's working around people who've been traumatized, that has an emotional effect on you as well. So consequently, listening to the stories of people who have had a very difficult time has an effect on the person who's listening to those stories. It's called compassion fatigue. Over time, you just get worn out from that misery. But there's a flip side to that, which is called compassion satisfaction. This is the idea that in helping people, you feel better. So is the consequence of helping people who've been traumatized compassion fatigue, or is it compassion satisfaction, or some combination of both? And that's what we're going to begin to look at in this model. I'm going to pick up where we did last time with just that singular model where we had started by checking assumptions. And in this example, I'm going to show you the output from JASP and show you how the assumptions, what the assumptions are, and then how they are tested. We have a dependent variable that's going to go on the y-axis, and all of our predictors, such as they are, would go on an x-axis if we were predicting one at a time. So our dependent variable has to be scale level, has to be measured on some kind of scale. If we leave the dependent variable in the same units as it was originally measured, it can be really easy to interpret. We can say things like, for every unit of increase in these predictors, we see a 1 pound decrease in weight, or a $1 increase in income, or a 10-point change in this variable that we're measuring. So our dependent variable, we're going to try to leave it in the same scale as it was originally. And we'll do that with the unstandardized coefficients. I'll also show you how we use the standardized coefficients. Those are for comparing within the model. And then your independent variable, or independent variables, because if we have multiple independent variables, we have a multiple regression, also need to be scale level. There are forms of regression where we can use categorical variables like nominal or ordinal. We're not going to do those now, but there are ways that we can do that. So for this example, we're going to restrict it just to scale level independent variables. I want to review the assumptions that are built into regression and how we would check those in the output. So the first assumption is that we don't have any outliers in either our independent variable or our dependent variable. And there are ways of checking this. We could do a scatter diagram or scatter plot. We can look for leverage values or independent cases, influential cases. But one way that we can do that works really, really well is to use the residual statistics. So one of the things that we're asking for is give me the residual statistics. You can get that in SPSS or in JASP. Go to the standardized residuals. These are like z-scores. So if they are too far away from 0, that tells us that we have an influential case or an outlier we'd want to address. So the numbers that we're looking for here are negative 3.29 and positive 3.29. As long as our minimum and maximum, standardized residuals, are within those boundaries, then we don't have any outliers that we need to worry about. So assumptions for outliers, check your standardized residuals. Another assumption is normality. And the best way to measure this in a multiple regression is to look at the standardized residuals. And this is something else that we ask for when we set up our regression equation. So we have asked for a QQ plot of the standardized residuals, and we've also plotted the residual errors against predicted errors, and we're going to use that for our next assumption check. So we look at our QQ plot. If we have normality of the residuals, we will see those dots lining up on that 45-degree line. And in this case, we do. It is not unusual that the dots will be off the line a little bit on the far extremes. So we see 2 up top and 1 at the bottom that are off the line by just a little bit. We're not going to worry about that. You see that for the most part, these dots are right on that line. So now the assumption of normality has been met based on a QQ plot, standardized residuals, and our evaluation of that plot. Now we have another plot here. It's the residuals versus predicted errors. We're going to use that to check the assumption for homoscedasticity. We want to know if the variability or the error around the predictors and the dependent variable is the same at all levels of the dependent variable. And the way that what we look for is in this residuals versus predicted, we have a roughly elliptical shape. If we had a cone shape, if we had something other than this cloud shape of dots, then we could worry about heteroscedasticity. But in this case, we see that the assumptions are well met for this. So there's our third assumption. Another assumption, independence of observations. We check that assumption using the Durbin-Watson statistic. The Durbin-Watson statistic is a test of autocorrelation. We want to make sure that our predictors are not too strongly correlated. If you have 2 predictors that are correlated at a 0.95, they are predicting pretty much the same thing. They are the same as predictors, so there's this tremendous overlap between their variability. We might as well just throw out one of them and use the other one. So what we want is to make sure that our predictors are predicting different amounts of variability in our model. They're not auto-correlated, and that's what we see here. We have this Durbin-Watson statistic that itself runs from 0 to 4, and we're looking for numbers close to 2. So we check our Durbin-Watson statistic. We see it's a 2.1. Great, that's close to 2. And there's also a p-value associated at a 0.5, not anywhere close to 0.05. Non-significant, this assumption has been met. Multicollinearity is tested with the tolerance and VIF statistics. These are actually the inverse of one another, so you'll see the same pattern in both of them. For these, we check the collinearity statistics. We just want to see that the VIF statistic, that's the larger of the 2, that should be less than 10. And the smaller one should be greater than 0.1. Now in this case, we've checked the collinearity of all 3 of the variables. We have burnout, compassion fatigue, compassion satisfaction, and for all of them, the collinearity statistics are the VIF is less than 10 and the tolerance is greater than 0.1. So again, this assumption has been met. So in all of these examples, there are assumptions to the test. We want to make sure those assumptions have been met. We definitely would include these in our write-up if we're going for publication. Probably want to include them regardless, because it shows that we know what we're doing, we know what the assumptions are, and we're conscientious to check those assumptions before we go on to do any model building. So in this case, we check our assumptions, all of them have been met, very good. Now what you can do is actually go back and rebuild the model, and you can actually turn off some of these checks if you really wanted to. Typically what I'll do is I'll build the first step of the model, and I'll include all of these checks, and then I'll go back and kind of start over and start adding the variables. So that's what we're going to do now. Do a multiple linear regression using JASP and this job satisfaction.sav data set, which we've downloaded, opened up in JASP. And we started last time building a model in which we used burnout to predict job satisfaction. Now in this slide, the top of the slide is the SPSS output, and the bottom of the slide is the JASP output. And what you can see is that the SPSS output has everything all in one place. So we have 1, 2, 3 models. We have the R squared for each of those. We have changes in R squared for each step along the way. When we are doing this in JASP, we just build them one step at a time. So we'll build the first model, and then we'll actually add that back in and call it the null model, and we'll build a second model, and then we'll add that, and we'll build a third model. Just go step by step. So we will see these results change, and they will always match up with the SPSS output. With some small variance, like for instance, the Durbin-Watson statistic for the JASP model is a 2.073, and for SPSS it was calculated at 2.103. Same result, but the numbers are just slightly different, and that has to do with the variability or the way that the particular test statistic is calculated. All right, so here we have, with our model 1 in JASP, we have only burnout predicting job satisfaction. When we look at the R value, this is the correlation, that R value, 0.65, that would be the same as our B coefficient as we build our model, or our unstandardized coefficient. That's what the correlation R and the B value is the same when we have just one predictor. Now the rest of these don't really tell us a lot. For instance, the F change or the R squared change, those are just being created comparing to nothing. If all we did was use the mean as our predictor, how much better could we do by adding burnout as a predictor? But being better than nothing, we know model 1 is a good model. What if we add another variable? So what we would do in JASP is we would create a second model where we'd add compassion fatigue. So we now just move that into the covariance window. And then the first option underneath the windows is the one for model. And in that we would simply add burnout to our null model. So we're now making burnout as a predictor our starting point, which was of course model 1. So now we have added a second model. Now the only thing that gets confusing here, I'm calling this model 2, but in the output we just have model 0 and model 1. So you can think of model 0, the null model, as being our starting point, and model 1 as being the model we're comparing it to. If you want to know what's in the null model, or model 0, you can see the note underneath that says null model includes burnout. So that note explains what is in each block of our model. Let's look at the R squared change and the significance of that at each step. When we look at model 1, which is really our model 2, we see that it's predicting the R is a little bit stronger. It's a 0.665. The R squared, still a little bit better, 0.442. And the R squared change is a value of 0.019, which might seem like a pretty small amount, but when we check the statistics for that, the F change in that, we're going to see that this is a better model than just including burnout. So what we're going to look at now is if we add a third variable, will that improve the model? Will it change the model? And that third variable is going to be the compassion satisfaction variable. So we have burnout and compassion fatigue already in the model. We're going to add one more variable. So the way we do that is we just reopen JASP and we move our third variable into the covariates box. We add, in the model section, we add the existing variables, which in this case are burnout, compassion fatigue, into the null model. So now that becomes our null comparison. We're going to do model 3, which again, in this output comes out as model 1. But we're going to use our third comparison and see, does it get any better? So now we're looking at the model summary for model 1. Now the R value has gone from 0.665 to a 667. So it's improved by 2/1000th of a point. And our R squared has barely changed. In fact, when we look at the R squared change value, we see just a tiny change in R squared, 0.003. The F value has changed by less than a point. And you see the P value of 0.335, that's non-significant. So what that tells us is that model 1, our first model, which just included burnout, that was a huge improvement over nothing. So we're going to keep that model. Model 2, where we added burnout and compassion fatigue, that was better than just burnout alone. So that model was good. We should keep that one. Model 3, however, where we add in compassion satisfaction, we didn't see much of a change. So there is a non-significant change in the predictors. So we're not going to use that third predictor after all. We're going to take that out of the model, and we're going to return to the model that was the best, which was model 2. So what we want is a model that is parsimonious. In other words, it predicts the most amount of variability with the fewest number of predictors. And that is model 2. So we've selected model 2 as our best model. As we look at the results, we can see our degrees of freedom for our ANOVA. We have our first degree of freedom, that's degrees of freedom between. We're using 2 comparisons. Here's our degrees of freedom within. And this gives us an F value we interpret. And our probability less than 0.001. So this model is predicting very well. This is the model that we're going to settle on, so it's model number 2. Let's look at our coefficients for this model that we have settled on as being the one that works best. Remember the prediction for a straight line is y equals a plus bx, where a is our constant or our intercept. So the intercept is right here, it's 222.645, that's our a value. The predictors, the unstandardized predictors for burnout, it's a negative 2.4, and for compassion fatigue is a 0.603. Now we would not include a predictor for compassion satisfaction, our third variable, because we're not including that in our model. The t values that we see here are telling us, by being statistically significant, that adding this next variable, in this case compassion fatigue, improves the model. So we have a better model by adding this new variable. And here's how we would write up our prediction. If I want to predict your job satisfaction, I would start with the value of 222.65, and then I would subtract your burnout score, which is 2.45, times the score that you got on the burnout scale. And then I would add back a 0.60 times the score you got on the compassion fatigue scale. And then the unknown error quantity, which I wouldn't actually add to it. I would just know that it was there. There's going to be some amount of error. So my prediction of your job satisfaction is probably going to be slightly off from your actual job satisfaction, and that's the error factor that is built in. So that's how to create my predictive model. I would work with it. So there's a few other bits of the output that we'd want to take a look at. The descriptive statistics, here we get the mean and standard deviation, standard error of the mean for each of the variables. We have an n of 200, so we have no missing values. That's going to be an excellent thing to see in any predictive model. And then in the collinearity diagnostics, this is something we looked at already, but I just wanted to leave it in as something to reference because you'll see that in the output. This is going to be useful for our write-up. See that use that later. We would conclude that job satisfaction is best predicted by using your burnout score and your compassion fatigue score, using our predictive model, and we would then be able to predict any given job satisfaction score based on what we know from burnout and compassion fatigue. And we know that adding compassion satisfaction then does not really improve our predictive model. All right. So there's one last idea that I want to share with you. It's about the model entry methods. You will see, whether it's SPSS or JASP or really any other of the statistical software packages that we could use, you will see options for how the variables should be put into the model. So I'm using a method called enter. It's where we put any variable in. So in this case, all variables going in at once. Right? We're just using that as our prediction, we're using that as our model entry method. So in that last example, I just put all three of the variables in and we saw what happened. Okay. This is usually the best approach. It is the default approach for SPSS and for JASP. But there are some other options that you'd want to know about. For instance, we could take our three variables and we could put them in one at a time and see if they improve the model. That's called a forward entry method. Or we could put all the variables in and then take one out, and take the other one out, and then take the third one out, and see what happens if we use a backward entry method. A stepwise uses the forward and backwards procedures to put something in and test it, and then maybe take it out, put another one in. It's really building the model based upon the strengths of the correlations between the variables. Now that may seem like an excellent idea. I just want to use the variables that are most strongly correlated because they're going to predict the most variability. But the problem with letting the math guide the model entry is that that may not line up with reality. It may be that according to our understanding of how people work or how a business works, that one thing always happens first. And then following from that, we have other. So what we might want to do is put that variable in first, even though it's not as strongly correlated, even though there's others that are more strongly correlated. There's one based on our model theory that really ought to go in first. And then we're going to add a second and a third. And the problem with stepwise is by just relying on the math to do all of your modeling for you, you can lead to deceptive outcomes or things that it tells you one thing but it doesn't really match up with reality. So this is generally considered to be the worst approach for modeling. If you try to publish a regression equation with this stepwise approach, sometimes they laugh at you. So I'd encourage you not to use that one. It's okay if you're trying to explore a model, but for the actual modeling, when you're actually putting it together for publication, you as a researcher deciding which variables to include and in what order is usually the best way to go. The last of the model entry methods is called remove, which have everything entered at once, and then you decide which ones to take out. Again, I usually use that enter method because it gives me the most control, and I can decide specifically how I want the model to be built based upon the specifications of reality and theory. Well, that is what I wanted to tell you about multiple linear regression and interpreting the output. Do you have any questions before we wrap up? So unit test 3 is available now, as is the study guide. I would encourage you to get the study guide now and fill that out, make sure you understand what's going to be on that test. But the test itself is not due for, well, at this point, because this is Monday, almost 2 weeks. So we have a full 2 weeks for you to continue to study, and then be sure you get it done by the end of week 13, this being week 12. Thank you all for being here. Thank you, everyone. Thank you so much for being here. I'll see you next week.
Don't neglect to clean your data as you ought, or just start creating descriptives, means, and plots. Your outcomes will be better Once you know just what you've got, then choose from 50 ways to run your data. 50 ways to run your data.